Right, here's a batch of thermodynamics questions and maybe a few other things related to it as well. So we've got lasers are often used to form precision welded joints in titanium. To form one such joint, it is first necessary to increase the temperature of the titanium to its melting point. Yep, figure 5.1 shows the joint and the volume of titanium to be heated. Right, okay, so we're heating up this grey area. The photon beam from the laser is focused onto the shaded volume of the joint. Oh yeah, so a volume, not an area, is converted into thermal energy in the titanium. Right, okay, so that's not really the sort of language that I would use to describe it, maybe. But so you'd say, well, the photon beam is heating the joint, so there's that transfer of energy. I don't really like this idea of thermal energy converted into thermal energy. I mean, that's the internal energy of the titanium is what we're talking about. So this is going to be, again, the kinetic energy and the potential energy of the constituent atoms in this metal. But still, we know what they're getting at, and this is part of the thing, particularly when we're talking about energy nowadays. There's so many different ways of describing it. The old school way about talking about forms of energy, which I'm not a big fan of, unless you're just saying it's kinetic energy and a potential energy, versus the more sort of maybe modern, more recent way of describing things, at least in schools, in terms of energy stores and transfers. So yeah, you have to get used to these different ways of it being described, because even if you are wedded to one type of description, you're always going to come across the other. Anyway, so part A, the wavelength of the photons is that. Show that the energy of a photon is 1.8 times 10 to the 19. Right, so I know this isn't part of our thermodynamics, but the energy of a photon is the Planck constant multiplied by the frequency, which is the Planck constant multiplied by the speed of light divided by the wavelength. So that is going to give us 6.63 times 10 to the minus 34 for the Planck constant, multiplied by 3 times 10 to the 8 for speed of light, and they've given us a wavelength of 1.1 times 10 to the minus 6. So this is going to be, well, we're adding 14 on there, so we've got minus 26.6 pretty much divided by 1.1, so that's 6 times 3, 18, so 1.8 times 10 to the minus 19 joules. If I put it in the calculator just so we've got something a little bit more accurate, if we're going to, yeah, it looks like we're reusing this in B, so 1.808. So we might want to use that for further calculations. Right, photons are emitted from the laser at a constant rate of 6.3 times 10 to the 19 per second. Estimate the time taken to raise the temperature of the shaded volume of titanium shown in the figure to the melting point. Right, so we're doing a mc delta T. So our energy, assuming it's all going into this, is going to be mc delta T. So what have they given us? Assuming we've got no losses going on here. They've given us, right, we've got a volume and a density, so we're going to have to change that to density times volume times C times delta T. We've got all of those bits. So our density is 4.5 times 10 to the 3. Our volume is 8.1 times 10 to the minus 12. Our C is 520. And our delta T is, what it's doing, it's going from 20 up to 1700. So 1680. So that is all of the energy that's put in. And we are getting energy, so our power, this is our rate of energy transfer, is going to be equal to what we worked out in the previous bit, 1.808 times 10 to the minus 19, multiplied by 6.3 times 10 to the 19. So they're going to cancel out, so that makes things a little bit easier. So that gives 11.34 watts. So now all we've got to do is divide our energy by the watts to get a time. So the time is going to be equal to our energy divided by our power. So just got to type all this in really. And this is going to come out at 2.8 times 10 to the minus 3 seconds. So that's good. So it's pretty quick. That's well, I suppose it's only a small volume and there's not much heating that needs to be done, but they clearly got a laser fit for the purpose. C, in practice, it takes a longer time to reach the melting point. State and explain 2 factors that will increase the time taken. Okay, so, well, the first one is, of course, we're going to have inefficiencies in this. We're going to have some kind of, well, all of it is going to be to do with inefficiencies, which is why it's taking longer. Now, there's 2 that spring to mind here. So we've got the energy supply is not what we're expecting it to be, as in not all of the energy from the laser is going into this joint. So that might be because we've got reflection or non-absorption at the joint, of reflection, non-absorption of laser beam. So that's one thing, because then we've got less going in. We'll have a lower effective power on this. So that's one thing. Or the other thing that we've got is, you know, heat being radiated away in some fashion, heat being lost from that joint. Now, considering the specific heat capacity of titanium, this is mostly going to be conduction outside of the heated zone. So we could say conduction to other parts of titanium. I'm going to run out of space. So, but yeah, the other parts of the titanium outside of that shaded area. So that is going to be a greater loss than radiation back to the air. So, because, you know, it's a metal, isn't it? So this is going to conduct the heat away pretty quickly. So let's go with those 2. Right, to complete the world, more photons must be focused onto the joint. Okay, during this final stage, the temperature remains constant. Explain why this is expected. Right, so this is where we've got the actual welding bit happening. So we've got to get it up to the melting point, but then we need to actually melt it. So it's all, you know, I don't know if amalgamated is the right word, but yeah, we need to get it to actually merge together. We need to get it into the liquid form. So it's one thing getting it up to the melting point, but this is what happens when we get a change in our phase of matter. So we're going from solid to liquid. So here we've got the energy is going into the potential energy. It's potential energy that's increasing, not the kinetic energy, which means the temperature will remain the same. This is, I suppose, another way of putting it is we've got latent heat of fusion going on here. So, and in our latent heat phases, in our transition from one phase of matter to another, we're not getting temperature rises. So that's quite a simple one to finish on. So yeah, it's quite a nice question. We've got an involved calculation, or with lots of steps at least. None of the steps are particularly difficult, but we just need to make sure we're doing everything in the right order when we've got so many numbers. And yeah, a little bit of conceptual stuff at the end. So that's a nice one to get started. Okay, so pushing on, we've got figure 6.1 here, which shows how the volume V of a fixed mass of an ideal gas at constant pressure varies with temperature. Okay, so describe how this graph leads to the concept of an absolute zero of temperature. Right, well, we can use this graph because they've given us a lot of space here on the left-hand side. So we can extend back this straight line. And I'm not going to write out every word of the explanation because it always takes too long to write it out. But you want to say, yeah, we can extend back this linear relationship between volume and temperature back to, well, either a zero volume or a negligible volume, because if we're going to get down to the lowest possible pressure, this is the minimum of our pressure is going to occur at a minimum of a volume where the particles in the gas are barely moving. So you want to make some statement about that. We can say that there's going to be a minimum volume that you can compress the gas down to, where it's got the least energy. So you'll be able to get it into that smallest volume when it's got the smallest energy. So I suppose the two things that we're going to say is, one, we want to extend the linear relationship between the volume and temperature. And then this idea that we've got a minimum volume, which is close to zero at minimum energy. And that is what we refer to as absolute zero, our 0 Kelvin. So, yep, that's what we got there. Part B, a mass of gas is enclosed in a tank. The gas is cooled until it becomes a liquid. During this process, its internal energy changes. State what is meant by the internal energy of a gas. So it is the sum of the kinetic energy and potential energy of the particles in the gas. So that's good. Then explain why the internal energy of the gas differs from that of its liquid phase. Right, so in the gas, we've got the potential energy is pretty much equal to zero. It's not going to be exactly equal to zero, but it's pretty close to it. And we can also say that the gas will have higher kinetic energy than in the liquid because the temperature is higher. So you can say those two things about it. So this is all good. We've all started off conceptually at the moment. This looks like with all the numbers here, we get them to calculations. So a scuba diver uses air in which the percentage of nitrogen is reduced by adding helium to form a substance known as trimix. So we've got that volume diving tank containing 45 moles of air, temperature of 20 degrees T. Calculate degrees C. Calculate the pressure in the tank. Right. So I've already used up quite a lot of space here, so I'm going to go back up here, and we've got our PV equals nRT. So because we're dealing in moles here rather than the number of particles, we've got 45 moles. So we're trying to work out the pressure. So the pressure will be equal to the number of moles, which is 45, multiplied by our gas constant, which is 8.31. multiplied by the temperature, which is 273 plus 20, so 293, and then divide by the volume, which is 1.2 times 10 to the minus 2. So off to the calculator we go with all of those numbers, and that is coming out with, I'm nearly there, 9.1306, so 9.1 times 10 to the 6 pascals. So good. Tank is then connected to a cylinder of volume that, so the smaller cylinder that we've got over here on the diagram, containing helium, that pressure, that temperature. The valve is opened, allowing the gases to mix. When mixed, the final temperature is still the same, yeah, because everything was at 20 degrees. Calculate the final pressure. Right, so we need to get the number of moles. That's what we haven't got here in the helium cylinder. They've given us the, what we got? We got the V, we got the T, we got the P, but we haven't got the N. So that's what we need to calculate first on this. So our N is going to be equal to PV divided by RT. The pressure is 5 times 10 to the 7. Our V is, what is it, 2 times 10 to the minus 3. R is R, so 8.31, and T is 293 again. So we need to put all of that in to get our moles, which is 41 moles, right? So we've got 41 moles. So now when it's combined, we can do the final pressure. So we're doing this calculation again, but we're just changing a couple of the numbers. So we're changing the 45 to 86 because that's the total number of moles. So we're going to have 86 times 8.31. The temperature is unchanged, 293. The volume has changed because we've got 1.2 times 10 to the minus 2 plus 2 times 10 to the minus 3. So that would be 1.4 times 10 to the minus 2. So we just type all of that in, and then we've got a new pressure. That's 1.49568. Blah, 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 blah. So 1.5 times 10 to the 7 pascals there for the pressure. So that's good. Part 3, last part. Explain why you would expect this pressure to decrease when the tank is used by a diver in water where the temperature is 4 degrees C. Well, we can say pressure is proportional to temperature if N and V are constant. So we can just go straight in for one of our gas laws and say that. I mean, it's really that the temperature as well. I mean, another way of putting it, the temperature is related to the kinetic energy, the average kinetic energy of the particles in the gas. So if you decrease the temperature, you're decreasing the average kinetic energy, which means you're going to decrease the pressure because they're colliding with the outside of the tank, or the inside of the tank, I suppose. It really is the inside, isn't it, of the tank? So they're colliding with the surface of the interior of the tank at a lower velocity. So you're going to get a smaller momentum change, which means you're going to get a smaller force, which means you're going to get a smaller pressure. So that's what's happening there. But we just got that relationship between P and T. So yeah, another nice mix of conceptual and calculation work there. Right, so finally in this block, this looks like it's going to be an experiment question because there's very little here. You're provided with a small bottle of cooking oil and standard physics laboratory equipment. Okay, whatever you're used to in a standard laboratory. Maybe my laboratory is particularly plush. You, with the help of a label diagram, describe an electrical experiment to determine the specific heat capacity of the oil. State 2 sources of uncertainty and how they could be reduced. Right, well, let's start with our setup then. So we're going to want to put the oil in some kind of insulated container. So let's start off with this. So we'll have to label all of this, but let's label it as we go along. Right, so this is the oil. This is the insulated container. Then we need the heater to go in it. So we'll have some kind of electrical heater in here, which can come out. So there we've got that bit. We'll connect that up in a minute. So this is the electrical heater. We'll need a thermometer. So we can put that in over here. Thermometer, which we'll have to again label. I'll just call it a therm just to make it quicker typing all this out. Let's have a stirrer in here as well. We always need a stirrer. I don't really know how to draw a stirrer, but if we label it, this will come in for our sources of excuse me, our sources of uncertainty. So we've got all of that. Yep, so that's going to be fine for that bit. Now we need to connect this up. We're going to need to go off to a power supply. So let's put that in. We're going to need an ammeter because we're going to need to know what the current is. We're also going to need the voltage across the heater. So let's just whack that in parallel. Just stick that on there. It doesn't really matter too much where you put it. So yeah, we got all that set up. That's looking pretty good. Now we need to say all the things that you're going to measure. So let's measure the mass of oil. We should put this into some kind of sentence. But yeah, we're saying measure mass of oil, the what we got, the current, which we'll call I. We got the voltage, or more to the point, the PD across heater, which we will call V. we need to measure the change in the temperature. So that is final temperature minus the starting temperature. That's good. What else have we got to do? We need to measure T, the time of heating. So we need to put all of those measurements in. So we're already racking up quite a lot of marks here for all the things we're saying. Then we can say that the energy supplied is going to be the power times the time, which is equal to V times I times the time. And that then is also, well, we can say that the specific heat capacity, which is what we're after, is the energy divided by the mass times delta T. So all in all, well, it's VI little t over M delta T. So that's the calculation we have to do. So we got a lot of marks from all of this. And then state 2 sources of uncertainty in your measurements and discuss how these could be reduced. So, well, we got the stirring one. That's why we put the stirrer there. So we can say uneven temperature in oil makes our temperature readings inaccurate. T inaccurate. Obviously put it into sentences. So our solution for that is use the stirrer, which leads to more uniform T. So that's one good thing that we could have there. We could have something about the container. So we could say, well, let's get the heat capacity of the specific heat capacity for the container and include in the calculations. So that would be something, you know, you could work out that bit. What else could we say? We could say that there is, well, there's a delay, isn't there, on thermometers? They don't just instantly go to the temperature that you want. So we could say that there's something with, I know we only have to do 2, but a third one is an option. So the temperature delay. So we could say, let's record the maximum temperature after we've turned the heater off, after heater turned off, and then we can use that in the calculation. Because otherwise, if you turn the heater off and just say, oh, what was the temperature then, you still haven't got the full effect. Even if we're stirring it, you're not going to have transferred all of that heat throughout the oil. It's not, and into the thermometer. So yeah, if you hang on a little bit, the temperature will keep going up and you'll get a much better final temperature measurement. So all in all, we've done a lot there. We've drawn this relatively detailed diagram. We've said 5 things that we're going to measure. We've got a calculation which is in 2 bits because we've got that bit and that bit. And then we've got a couple of different ways of improving the experimental procedure. So yeah, this could be, they probably only give out 6, 7, 8 marks for this, but we've said about 12 things there. So it's going to be very easy to pick up the full set of marks. It's the same old thing with all these experimental ones. You get a practical question, just be step by step. Say what all the equipment is, how you're going to use it, what you're measuring, what you're calculating. It's just gimme marks, really. And nothing is too obvious to write down in these things. It's amazing how, you know, they give out marks for just saying measure the mass of the oil. And a lot of people leave it out because it seems so obvious. I mean, what else are you going to do? But you still have to say it. It's part of your experimental procedure. It's something you would be doing in the experiment. So say that that is what you're going to be doing. You know, they can't quibble about it. It's something you're going to do. So you say it and they have to give you a mark for it. So don't think anything is going to be too obvious in these questions. Right, well, that brings us to the end of this block of 3. I've gone on long enough and we'll carry on in the next one with some more questions.